This lesson is over Algebra 2, Unit 4, Lesson 1, Part 2, or 4.1b, just depending on how it's labeled. Now, in the last lesson that we had, the first lesson in Unit 4, it was over solving quadratics, solving parabolas, and solving meant finding where that parabola crossed the x-axis, and we could have 0, 1, or up to 2 solutions, 2 places where a parabola can cross the x-axis. Now, what we learned last time is we could see those solutions by where the parabola crossed the x-axis. There's another way to do it, and that's algebraically, and that's by factoring. We're not really going to get into the solving part of the quadratics today. That will come in our next lesson because we need to review our factoring skills, okay? Factoring is such a huge part of Algebra 2. I know a lot of people do not like to factor. I think we all just need to learn to embrace it. I think it's super fun. It's like, can be a little bit of a challenge, but it's so satisfying when you do it right. And it's used not only a ton in this unit, but in tons of units in Algebra 2. It's used in pre-calc, it's used in calc, and it's just like one baby step of a process and bigger problems. So the sooner you learn to embrace factoring, the better off you will be in math. So factoring, one thing to remember is that factoring means to make it back to a multiplication problem, okay? You're turning it from a polynomial, something like a string of terms, back to a multiplication problem. Multiplication problem. So that means we need to have some parentheses or something to show that we need to multiply either by distributing or FOIL, something like that. So if you're looking at what we have here on numbers 1 and 2, on number 1 we have 12k minus 18. That right there is a binomial. I have just 2 different terms. It's not a multiplication. I can see that there's no showing to distribute or multiply anything. So to factor it, I'm going to turn it back into the multiplication problem. And a lot of times when we turn something back into a multiplication problem, we have to do that opposite operation. And the opposite operation of multiplication is division. So the first type of factoring that we have is in the set 1 is factoring by taking out the greatest common factor. Now this is always something you should check for first when you're doing any type of factoring. Okay, so let's look at what we have on number 1. 12k minus 18. I'm looking for the greatest common factor for the number parts first, 12 and 18. And we did do this in our Algebra 1 review. What's the largest number that goes into 12 and 18? Okay, a lot of times I told you check to see if the smaller number 12, see if that would go into 18, and it does not go into it evenly. So the number we are looking for is going to be lower than 12. So the next number that goes into 12 would be 6. So I checked, does 6 go into 12 and 18? Again, I'm using division now to turn this back into a multiplication problem, that inverse operation. So I drew that blue line underneath to show I'm going to divide 6 out of both these terms because that's the largest number that divides evenly into 12 and 18. Now I need to know, can I take any letters out as the GCF as well? To be a greatest common factor, it has to be common or part of both or all the factors or all the terms in the problem. So you notice we have a k here, but 18 does not have any k's. So k is not common to both these terms. We cannot pull a k out as the GCF. So we have 6 as the only part that's the GCF. Now that we know that, we're going to divide each of the terms above it by 6. And I usually show that by circling. I'm going to do 12k divided by 6 is 2k. And then I'm dividing the next term. Negative 18 divided by 6 is negative 3. Okay, that is the part we get when we divide. But that's still not a multiplication problem. So what we do is we wrap this up in parentheses and our GCF goes on the outside. Now if you check this out, this is our answer because it looks like, and it is, a distributive property problem now. We could test this. What is 6 times 2k minus 3? Like what the answer is. When you multiply out or distribute, you should always get back to your original answer. So 6 times 2k would be 12k. 6 times negative 3 is negative 18, which puts me back to this original problem that I have, so I know that I've done it correctly. So one of the beautiful things about algebra is that you can always check your work to see if you've done it correctly. It's like wonderful because you can know like, hey, I got like 100% because I checked my work, everything came out right. I love it. Okay, so on number 2, my binomial here is 40x to the 8th power y plus 64 x to the fourth y. So I'm looking, to factor this, I need to divide out the largest number and the most amount of letters that they share. So what would that be? What's the largest number that goes into 40 and 64? Now sometimes it's a trial and error process because I know that 40 does not go into 64 evenly. Okay, I would be thinking of different numbers. What goes into 40? I always look at what goes into my smaller number because we're limited by that smaller amount. 10, but 10 does not go into 64. I know that 8 goes into 40, so then I check, does 8 go into 64? So that's a pretty good idea that 8's the number portion of my GCF. And then I'm checking my variables. They both have x's, so x gets to be part of the GCF, but how many x's can we take out of both? We have 8 x's in our first term, 4 x's in our second term. So how many can they both give? If they both have to give the most that they possibly can, but they have to each give the same exact amount, then we're always limited by the amount that's the smaller, right? If 64 has 4 x's, because the exponent's telling you how many x's he has, he can't give more than what he has. He's only able to give 4. So that means that on my 40x to the 8th y term, that even though he has 8 x's, he can only give 4 because those two terms have to match. So I'm going to put x to the 4th here. And then I look at my y's. They each have 1 y. They have the same amount, so they can both give that same amount, 1 y. Okay, now our job is to divide 8x to the 4th y out. That is the GCF right there. But we have to divide it out of each of these terms. And that's going to be the portion that goes inside the parentheses. So we do 40 divided by 8 is 5. And then when we're dividing with variables, we subtract their exponents. So 8x's take away 4x's is 4x's left. So x to the 4th. Y take away a y means all the y's are gone. Okay. Then we move on to our second term. 64 divided by 8 is 8. X to the 4th, taking out x to the 4th, there's no more x's left. Y take away y, the y's are gone. So 5x to the 4th plus 8 is what goes inside the parentheses. My GCF always goes on the outside. 8x to the 4th y. Again, I could distribute this back out and I would get back to my original problem, and that would be a way to check to see if I've done it correctly. Okay, so continuing on with numbers 3 and 4, we are still factoring by taking out a greatest common factor. But on numbers 3 and 4, there are 3 terms in each of these problems. So you just have to make sure that the GCF is the GCF for all 3 instead of just 2 terms. So there's just more checking here. So on number 3, we have 14m to the 6th minus 35m cubed minus 7m squared. So I'm thinking, what's the largest number that can be pulled out or divided out from 14, 35, and 7? Okay, my smallest number here is 7, and I'm going to start by checking, can 7 go into 14? Yes, it can, and it can go into 35. If your smallest of all your options can go into everything else, then that will be the GCF. Okay, you don't have to look any lower than that. So, awesome. We have the number portion of our GCF. Now, what about our variables? They all these terms each have an m. So, if we have 6 m's here, 3, and then 2, how many can they all give? If they have to give the most possible, but all the same, they could all give 2 m's, right? We're limited by the smaller of all the choices. So 7m squared is our GCF. Now we have to divide it out of each of these terms. So 14 divided by 7 is 2, but remember our exponent rules, variables, exponents do something different than the regular numbers or than our coefficients. We subtract the exponents. So for m, we're going to have 6 minus 2 to have 2m to the 4th. We move on to our middle term. Negative 35 divided by 7 is negative 5. And then we have m's. We have 3 minus 2, which is 1m, which we can leave just like that. And then I have negative 7m squared divided by its own self, 7m squared. Anything divided by its own self is 1, and it's negative 1 because we got a negative divided by a positive. Now remember, that's just the portion that goes inside the parentheses. Our GCF always goes on the outside, 7m squared. That's our answer. Okay, number 4, we have 3ab squared minus 5a squared b plus 8ab. So I'm checking on my coefficients, 3, 5, and 8. Okay, what's the largest number that goes into all three of these coefficients? Well, let's see. Does 3 go into 5? No, 3 does not go into 8. And 3 has no other factors besides 1. 3 and 5 are both prime, by the way, too. So we don't have any numbers that can be divided out of all three of 3, 5, and 8. So we don't get to take any coefficients or numbers parts out as our GCF. That doesn't mean there's not a GCF. It just means that there won't be any numbers, regular numbers. Now we check our variables. Okay, they each have an A. Okay, we have 1A, 2 A's, and then 1A. So if 1 is our lowest exponent, that's the most we can take out. We can take out 1A. Then our B's, we have 2 B's, 1B, 1B. So again, what's that lowest exponent? It's 1. That's the most we can take out from everything is 1. So AB is our GCF. Even though they're just variables, they can still be the GCF here. So now we need to take 1A and 1B out of each of these terms. So we have 3AB squared, and we're taking away 1AB, and we're going to be left with 3 as our number, because we're dividing by 1. A take away A, no A's left. 2 B's take away 1B, we have 1B. So 3B is what we're left with. And then negative 5 divided by 1 stays negative 5. 2 A's take away 1A is 1A. B take away B, no B's left. Moving to our middle term, 8 divided by 1 is 8. And then an AB, taking away an AB means we don't have any AB's left. So it's just 8. Wrap it up, put your GCF of AB on the outside. This again is in factored form. It's a multiplication problem now. It looks like distributive property when we've just taken out a GCF. To check to see if you've done it correctly, you can multiply it back out. When we multiply with variables, remember we add exponents. So there you go. That's the GCF section. Okay, now we are in set 2 of our notes, and we are still factoring. We're still turning our polynomial expression back into a multiplication problem, because that's what factoring means. But now we're going to practice a different method of factoring. This is a method that we have used in the past. Okay, this is when you have what's called a quadratic trinomial. And what a quadratic trinomial is, it's when we have squared, an x squared, usually it could be a different variable, but we have squared as our highest exponent, and then we have 1, 2, 3 terms. That's a trinomial. And you've probably heard me say a million times by now that counting the number of terms when it comes to factoring is very important, because it can tell you which method to use. And I say a lot, and all of you can repeat after me. If I say 1, 2, 3 terms, 1, 2, 3, we do factor tree, which this factor tree is this little triangle that I've drawn underneath 45. The factor tree always goes underneath the last term, the constant. And when we do this factor tree, we're looking for two factors, two numbers, and factors are things that multiply together to make something else. So I am looking for two numbers that multiply to make 45. But those same two numbers, when I add them across, they always add to our b value, or the middle number, which in this case is positive 14. There's only two specific numbers that will work in this situation, okay? So that's why it's awesome, because it's not like you can just think of anything that multiplies to 45 or any random two numbers that add to 14. They have to fit what I call this puzzle both ways. They have to multiply to 45, they have to add to 14. So because we have a positive and a positive number that we are multiplying to and then adding to, the two factors will be positive as well. So that tends to make it a little bit easier when we're dealing with all positives. And I just start thinking, what multiplies to 45? The first things I think of are 9 and 5. So let's test that out. 9 times 5. 9 times 5 do make 45. I'm not done because I have to check to see if they add to 15 when I add across. 9 plus 5 make 14. All right, so the first two numbers I've thought of work. My two numbers are 9 and 5. Now what do I do with that? I'm, again, breaking this apart to be a multiplication problem. So I have to think, what makes x squared? Well, it's an x times an x. Okay, we have to show that somehow. So whenever you're doing a 1, 2, 3 factor tree type problem for factoring, it's going to be a FOIL-looking problem when you're done. If we get x squared by multiplying x times x, we would have 1x at the beginning of each set of parentheses, because when we would distribute, we would get that x times x, which would result in x squared. And then each of those two factors, 9 and 5, okay, they were both positive, so I just put 1 in each set of parentheses. We have a positive 9 and a positive 5. Again, this is done. The answer is x plus 9 times x plus 5. Nice, lovely FOIL problem. Again, you can still check this to see if you've done it correctly. If I multiplied it back out, x plus 9 times x plus 5, if I FOIL it, I'm going to get x squared plus 5x plus 9x plus 9 times 5 is 45. The middle two always combine, and so we have x squared plus 14x plus 45. So that's how I know I've done it correctly, because the answer I got multiplied back to the original. So can you see that these two parts of the problem, they have the same value, but they're just in different forms? Okay, we have basically a trinomial here, quadratic trinomial. It's like in standard form, and then we have factored form. Now each of these terms have their uses, and we're going to learn in our next lesson why factored form is so important. But for now, we're just practicing again this method of factoring because it will be built on later, this skill. So on number 6, notice again I have 1, 2, 3. I'm going to do my factor tree coming out of the last term. What are the specific two numbers that multiply to positive 26, but yet when I add those two factors, they add up to negative 15? So then I'm thinking, if I'm going to multiply to a positive and add to a negative, I'm looking for two negative numbers here. So what multiplies to 26? Well, I know that 26 is even, so that means it would be divisible by 2. 26 divided by 2 is 13, and I know that 13 and 2 make 15. So I feel like I'm on the right track here. And because I want positive 26 and it to add to negative 15, I'm going to say negative 13 and negative 2. Again, those two negatives do multiply to positive 26, check. And negative 13 subtracting to add to negative 15, or subtract to negative 15, however you want to think of it. So my two factors here, we have found them, negative 13 and negative 2. So again, I'm not done. I have to show that as a multiplication problem, so we make two sets of parentheses. If I'm doing a w squared as my leading term here, what makes a w squared is a w times a w. So I need one w at the beginning of each set of parentheses, and then I just drop each of these factors in after that, a minus 13 and a minus 2. Now order doesn't really matter which factor goes in which set of parentheses. We could also say w minus 2 and then w minus 13, and that's the same. Okay, they're both the correct answer. Okay, on number 7, I need to factor c squared plus 2c minus 48. So I think, oh, there's 1, 2, 3. I'm going to use factor tree to factor this. I'm looking for two numbers that multiply to negative 48 but add to positive 2. If I'm multiplying to a negative and adding to a positive, I'm looking for one number that's positive and one number that's negative. So when I find those two factors, I basically need to subtract them to see if their difference is 2. So what multiplies to 48? I'm like 4 times 12? 4 times 12 makes 48. But what happens when we subtract 4 and 12? Do they make 2? So I would check. Okay, again, you could test a lot of different things. 4 and I would say negative 4 and positive 12. Yes, that multiplies to negative 48, but negative 4 plus 12 equals 8, not 2. Okay, so that doesn't work. That's a sad face. So we have to go back and we have to try something else because those were not the right two numbers. Because again, they only fit half the puzzle, not the whole thing. So now I'm thinking, what else multiplies to 48? Well, I know that 6 and 8 multiply to 48. So I'm going to write down 6 and 8. And again, I know one has to be negative and one has to be positive. And it does matter which one's negative and which one's positive. Negative 6 times positive 8 multiply to negative 48. And negative 6 plus 8 make positive 2. If I had made the 8 negative and the 6 positive, we would have gotten negative 2, which would not be exactly right. And it does need to be exactly right to work. So I have found the right two factors, negative 6 and positive 8. So we make two sets of parentheses. If I'm dealing with c squared, that would be a c times a c. So I put one c in each set of parentheses, and I drop in my two factors, minus 6, positive 8. Or if the order was reversed, that would be the same thing as well. Okay, number 8. n squared minus n minus 72. Turn that back into a multiplication problem by factoring it. So 1, 2, 3, factor tree. Okay, and it says that we should always check for a GCF first. And the reason why I'm not taking a GCF first out of these, if you look on number 7, I have a coefficient of 1. There's nothing in front of c squared. And on number 8, it's a coefficient of 1, an implied 1 as well. There's nothing in front of n squared. If I don't have anything in front of my first term, my squared term, I don't have a GCF. Okay, because when 1 is the highest or lowest number, then there's nothing that can be pulled out of the rest. So what multiplies to negative 72 and adds to negative 1? That's my middle value, right? Negative n means negative 1. Let's put the negative sign there. So I am looking for two negative numbers here, or a negative and a positive, excuse me, to multiply to a negative. And if we're adding or subtracting to a negative, then the larger of our two factors will be negative as well. That's what I was kind of thinking of when I said two negatives. So what multiplies to 72? For me, I just think of 9 and 8 automatically. 9 and 8. Now, what if I said 9 minus 8? 9 times negative 8 would make negative 72, but that would subtract to positive 1. So we need to switch the signs here. Let's try negative 9 and positive 8. They still multiply to negative 72, but now when I add them across, negative 9 plus 8, they do make negative 1. So those are the right signs that would go with these two factors. We're dealing with n squared, so that'd be an n times an n. So when I make my parentheses, I need one n in the front of each set of parentheses, and I'm going to drop in negative 9 and positive 8 in the other one. This FOIL problem, when I FOILed it back out, it would get me back to the original problem. So we are done. Okay, number 9. We have a squared plus 12a plus 36 that we need to factor to turn back into a multiplication problem because I have 1, 2, 3. We're going to use factor tree to do this. I'm looking for two numbers that multiply to positive 36, and then those same two numbers have to add to 12. So what multiplies to 36? I know that 12 times 3 make 36, but 12 plus 3 would make 15, not 12. So we don't like that. It's not going to be 12 and 3. Okay, so what else multiplies to 36? Let's check. 6 times 6. 6 times 6 makes 36, and 6 plus 6 add to 12. So we've found our two numbers that we need. We'll make two sets of parentheses. To get a squared, we would have an a times an a, so we put one a in each set of parentheses, and then plus 6 and plus 6. Now, one thing we need to start recognizing is that when we have two of the same identical factors, a plus 6 is a factor. Okay, it's its own grouping, and it's being multiplied by another grouping of a plus 6, and they are the same. Okay, we're going to say these are the same. When you multiply anything by its own self, we can say it's squared. It's that value squared, right? So we could rewrite this as a plus 6 all being squared. That 2 right here means that there was two a plus 6 factors like we had above. So this is done. Okay, number 10, we have n squared minus 2n plus 1 that we are factoring. So two numbers that would multiply to positive 1 and add to negative 2. Well, there's only two numbers that multiply to 1, and that's 1 times 1. But if we need a negative 2 as our sum, I'm going to say it's negative 1 times negative 1, because they do multiply to a positive 1, and then they add across to negative 2. So if we're dealing with n squared, okay, that would be an n times an n. So we're putting one n in each set of parentheses, and minus 1, minus 1. Again, these factors, that what we have in the parentheses, in other words, are identical. So we have two of them. So 2 can be the exponent. We're going to say this is n minus 1 all being squared. Done. Okay, on number 11 and 12, we have a little bit different situation. On 11, we have 2k squared minus 16k minus 40. What's different about this problem is that I've got a number in front of my leading term here. I have a 2 in front of this k squared. On all of the other examples, if you look back, and I mentioned this on numbers 7 and 8, there was no number in front of our squared term, which means we did not have a GCF to take out. You can only do 1, 2, 3 factor tree if nothing is in front of that squared term, okay? We need a coefficient of 1. So it's really nice, first thing we check is, can we divide out that number as our GCF? Does 2 come out of all three of these terms? We know it comes out of its own self, and 2 can come out of negative 16, and it can come out of negative 40. So that's the first thing we're going to do. We're going to divide all three of these terms by 2. And that's, again, pulling it out as a GCF. So we divide it, we get k squared minus 8k in the middle, and then negative 40 divided by 2 is negative 20. And just like any time we take a GCF out of something, we have to put it on the outside. Okay, wrap up what we get in parentheses and put the GCF on the outside. Okay, we're not done. That was just like the first little baby step. Because I still have 1, 2, 3, I need to do factor tree now. And the reason why we can do it now is because there's nothing in front of k squared. We move that 2 to the outside of parentheses. That's what we were going for. So what are the two numbers that now multiply to negative 20, but yet add to negative 8? Okay, so what multiplies to negative 20? And I'm thinking, well, what about 5 and 4? But that would add to 9, so that doesn't work. So 10 and 2, they multiply to 20. Oh, that sounds like it could be pretty good. 10 and 2. Can I do a positive and negative combination to get that to add to 8? If I do negative 10 and positive 2, I would add up here to negative 8. So we are multiplying to negative 20, negative 10 times 2, and then their sum is negative 8. I've said that like 5 times, sorry. So we're going to leave this 2 on the outside. You do not lose your GCF. Okay, in math, we don't just magically like lose and gain values. We can rearrange. We can balance. We don't just magically let things vanish and disappear. So the GCF always stays on the outside. Now we have our 2 sets of parentheses. We were dealing with k squared, which is gotten by doing a k times a k, so 1k in each set. And then in one set of parentheses, we drop that negative 10, and the other one, the positive 2. So this whole thing is our answer. You should always check that your GCF is out front of your set of parentheses, that you didn't lose it. Okay, on number 12, we have 5z squared minus 25z plus 30. Because we have this 5 in front of z squared, that can't stay there if we want to factor it. So I'm going to check, does it come out of all three terms? It comes out of its own self, it divides into 25, and it divides into 30. So we can pull 5 out as a GCF. So that means we're dividing it out of all three terms. 5z squared divided by 5 is 1z squared. Negative 25z divided by 5 is negative 5z. And positive 30 divided by 5 is positive 6. Again, wrap it up when you're done dividing by the GCF, and that number has to go on the outside. And now we're dealing with 1, 2, 3 on the inside, factor tree. We're looking for two numbers that multiply to 6 but add to negative 5. Okay, multiplying to 6. Positive 6, but adding to a negative, we need two negative numbers. So negative 6 and negative 1 or positive 1 won't work. Okay, I know a lot of people are going to say, what about negative 6 and positive 1? These two look like they should work because I can see that negative 6 plus 1 do add to negative 5. But remember, it has to match exactly. Negative 6 times positive 1 would make negative 6. And we're trying to multiply to a positive. So that does not work exactly right. So those would not be our two factors here. All right, so we're going to move on and look for two different numbers that multiply to positive 6 but add to negative 5. Okay, 2 times 3. So if I did negative 2 times negative 3, we need a negative times a negative to make positive 6. And negative 2 subtract 3 adds to negative 5. So those would be the right two factors. Okay, the only two that will work. 5 is going to stay on the outside. We're not going to lose that GCF. We make two sets of parentheses. If we're doing z squared, we need to put one z in each set of parentheses. And we'll drop in our minus 2 and our minus 3. This is done. Okay, now we are in set 3. We are still working with trinomials, but what this is saying up here, we have ax squared plus bx plus c where our a value is greater than 1. The a value means the number in front of x squared, so that means we have a number larger than 1 in front of x squared. You can see a visible number, and what's going to be different from what we did on 11 and 12 is that number is not going to divide out as a GCF, okay? It won't. So we are going to use a method here on numbers 13 through 20. And this method we're going to refer to as, okay, slide, and then we divide, and then we simplify, and then we're going to say bottoms up. bottoms up. Okay, now when we slide, that means we're going to multiply. Okay, so let's talk about what all this means, but you'll hear me say it a lot. This is a slider. A lot of times I call these sliders. Let me make a note of that here. Okay, a slider. Okay, on number 13, we have 2x squared minus 15x plus 18. So what I'm noticing is that I've got this 2 in front of x squared. You can't factor when you've got a number in front of your squared variable. Now, what we did on number 11 and 12 is we were able to divide it out as a GCF from all three terms. But can we divide 2 out of all three of these? 2 goes into 2, but 2 will not go into 15, okay? It does not work here. So we can't pull 2 out as a GCF. So now we are limited on what we can do. We have to do something else to get rid of that 2. Otherwise, we can't factor. So this is what we're going to do, slide. That's your first step. What we're going to do is take the number in front of your squared value, that first term, and we're going to slide and multiply it to the C value, the last value. So slide means to multiply. When I slide it over, I'm taking it away from the squared term. So now it's just x squared. Then we have minus 15x. We haven't touched the middle term, but I said 2 times 18 is now positive 36. Okay, we multiplied if you can't see that time side. Now, we're going to have to undo that later. But for now, we've removed it in front of the x squared. We removed it legally so that now we have a real 1, 2, 3. We can do our factor tree here. So we're looking for two numbers that multiply to positive 36 and add to the middle term, negative 15. What are those two numbers? Well, I'm thinking it's not 9 and 4. They don't make 15. They would make 13. So let's think again. And I'm going to think 12 and 3. Okay, and they both would need to be negative. Negative 12 and negative 3. They multiply to positive 36, and negative 12 and negative 3 add to negative 15. So same as I did before, now we're going to put it in parentheses. Okay, we're still just doing that slide and multiply step. If we had x squared, we're putting 1x in front of each set of parentheses. And then we're going to drop in our minus 12 and our minus 3. Okay, so see how, remember how up here at the top we did this whole sliding thing? Okay, to keep this all balanced out, we have to account for that. And we have to put it back into place. So we're going to do what we call divide now. We have to divide each of these factors, the 12 and the 3 that I just underlined, by the number that we slid over. So we slid the 2, so now we're going to divide each of these by 2. Now we need to simplify each of these terms. I'm going to look, can we simplify 12 over 2? Yes, that simplifies to 6. So we're going to rewrite this factor as x minus 6. But when I look here at negative 3 over 2, that does not simplify anymore. But when it comes to factoring, you never leave like a fraction inside the parentheses if you can help it. So this is, we did our simplify. It does, if it was going to be a fraction, so we would need to simplify the fraction. We'll talk about that more later. But now we do what's called bottoms up. The number that's in the bottom part of the fraction, the denominator, needs to stay in its own set of parentheses, but it's going to go up in front of the x that's with it in the parentheses. So that 2 is going to go bottoms up in front of x, so that we have 2x minus 3. Look at, okay, so this is the answer we were looking for. If I FOILed this back out, I would get back to the original. And if you don't believe me, you can test it on your own. This video is going to be long enough as it is. Okay, so moving on to number 14. We have 5p squared plus 22p minus 48. So my issue, again, is this 5 that's in front of p squared. It will not divide away. So we're going to have to do these steps again. We're going to have to slide it away. So we're going to take this 5, and I'm going to slide it over and multiply it to negative 48. So that's going to leave p squared by itself. We have plus 22p still in the middle term, and then 5 times negative 48 makes negative 240. Now, when you are dealing with a larger C value, it does sometimes make it a little bit harder to figure out what your two numbers are. It doesn't happen a lot, but right now we can do 1, 2, 3 factor tree. The two numbers we're looking for need to multiply to negative 240 and add to positive 22. And I don't know, I'm just thinking, like I'm kind of thinking of 24 here because it's the first part of the 240. And I know 8 times 3 makes 24, so let's see if 30 times 8. Okay, so we're going to say 30 and then 8, and I need one to be positive and one to be negative. So 30 times negative 8 is negative 240, and 30 minus 8 is positive 22. And in class, when we have calculators, because I can't show a calculator on this video, I would go over what we will do trial and error for you to figure that out. But a lot of times it takes taking that C value, that constant, and just by trial and error, start dividing it by numbers. Now, if you get a whole number answer, you've found a factor, and try like adding, subtracting those factors that you get real quick to see if they combine to make your middle term. Again, I'll show that better in class, but it's really hard to do on this video. So we'll just do a little bit quicker. So in the parentheses, we'll drop down these two factors. We're going to have p plus 30 and p minus 8. Okay, so that we had just done the slide and the factoring. Now we have to undo the slide by dividing by the number we slid. We're dividing each of these factors by 5. And now we have to simplify each of these factors. So can we simplify 30 over 5? And yes, 30 over 5 makes 6. So we have a factor of p plus 6. It doesn't have a bottom, so we won't have any bottoms up there. And now I'm looking at negative 8 over 5. As a fraction, that does not simplify anymore. And what I'm saying is if like you had 3 over 6, before you could do bottoms up, you would need to simplify it to 1/2 and then do bottoms up. We simplify first. Because this doesn't simplify anymore, I'm going to take my bottom number 5 and bring it up in front of p so that this is 5p minus 8. And we're finished. Okay, number 15, our trinomial is 3h squared minus 19h minus 40. Okay, I have to recognize, we need to recognize that there's a 3 in front of h squared. I would check, does it divide into 19 and 40? It does not divide into those terms, so we have a slider. We're going to take this 3. We have to move it legally by sliding and multiplying it to negative 40. When we slide it, again, that makes the h squared by itself. We didn't touch the middle term, so it's still minus 19h, and 3 times negative 40 is negative 120. So when we do our 1, 2, 3 factor tree, we're looking for two numbers that multiply to negative 120 and add to negative 19. Okay, and again, this might be trial and error, but don't give up. The more you practice, the better you will get at this, and it becomes faster, I promise. But those two numbers are going to be negative 24 and a positive 5. That multiply to negative 120, and then you add to negative 19. So we're going to write it in parentheses as h minus 24 and h plus 5. So that was the slide. Then we have, and the multiply. Now we have to divide by the number we slid. We're dividing each of these two numbers by 3. So now we have to simplify before we do bottoms up. So looking here, negative 24 divided by 3 makes negative 8. So we have h minus 8. And then 5/3, I would check to see if it could simplify as a fraction. So since it does not divide evenly, it does not. So 3 goes bottoms up. It goes in front of its own h. So we have 3h plus 5. Okay, and that's finished. Number 16, we have 12x squared plus 5 minus 2. Okay, 12 in front of the x squared, and that 12 will not divide out of 5 or 2. So we have to slide it over to move it so that this can be factored. So we will have x squared plus 5x minus 24. That's 12 times 2. So now we do our 1, 2, 3 factor tree, two numbers that multiply to negative 24 and add to 5. And for some reason, for a lot of students, when you're working with smaller factors, it's easier to find those two numbers. What multiplies to negative 24 and adds to 5 would be 8 times negative 3, because that multiplies negative 24. 8 minus 3 is 5. So we have 8x plus 8, times x minus 3. Okay, and that was the slide. Now we have to divide. We're dividing by the number we slid, so we're dividing each of these by 12. So slide, divide, simplify. Okay, simplifying 8 over 12. That simplifies as a fraction. 8 over 12 simplifies to 2/3. 3 over 12 also simplifies, okay? We can't do bottoms up till we simplify. 3/12 is the same thing simplified as -1/4. So there we go with our simplifying. Now we can do bottoms up. The 3 on bottom comes up in front of its x, so that we have 3x plus 2. And the 4 on the bottom of x comes up, or on the bottom comes up in front of its own x, excuse me, and we have 4x minus 1. It's getting very late here. So this is finished. We had 2 bottoms up, and that can happen. It's finished. Okay, 17, we are factoring the trinomial 6y squared minus 5y minus 21. So my 6, my leading coefficient here, larger than 1, I check to see if it will divide out. Does not divide out of 5 or 21, so we're going to be sliding and multiplying it over to -21, so that we have y squared minus 5y, and 6 times -21 is -126. So we do 1, 2, 3 factor tree now. We're multiplying to -126 and adding to -5. Okay, the two numbers that do this will be -14 and +9. So we write it in factored form. We have y minus 14, y plus 9, and then now we're doing the rest. We already did the slide, then I guess the next step should technically be factor. And now we have to divide. Divide each of your factors by the number you slid and multiplied by, so by 6. Simplify is your next step. What does 14 over 6 simplify to? And you could check that on your calculator if you need to. But that makes -7/3. And then 9 over 6 makes positive 3/2. Okay, so we simplify our fractions, and then last we do anything on the bottom comes up in front of its variable inside its own set of parentheses. So we're going to have 3y minus 7 times 2y plus 3. And if you're ever not sure, you can always multiply it back out to see if you get back to your original problem. Okay, so on number 18, we're going to get a little something different here as well. We have 16m squared plus 60m minus 54. So I'm checking, okay, we've got this 16 in front of m squared. Now, while 16 itself will not go into 60 and 54, I recognize that all 3 of these terms are even. Okay, every even number is divisible by 2. So I can at least pull a 2 out as a GCF. So I'm going to divide 2 out of everything. 16m squared divided by 2 gives me 8m squared, and then we have plus 30m. And -54 divided by 2 is -27. And then I would wrap it back up and put my GCF here out front. Now, I did have a GCF. That step needed to happen, but notice we still have this 8 in front of the m squared. So we still have to remove that 8. So this is still going to be a slider. Okay, so it was a GCF and a slider. How lucky are we? So what we're going to have now, we have 2 on the outside of the parentheses, and then inside, because we've removed the 8 to multiply over, we're going to have m squared plus 30m, and 8 times -27 is -216. And then close it back up. So now we're ready to do 1, 2, 3 factor tree. We're looking for 2 numbers that multiply to -216, but yet add to positive 30. Okay, those 2 numbers would be 36 and -6. So 36 times -6 work here. They multiply -216, and 36 minus 6 is 30. Again, trial and error. I'm doing it faster because it's a video. We'll practice the trial and error more in class. So we have 2, and then parentheses, we have m plus 36, parentheses, m minus 6. So that was our factoring, and now we need to undo our slide by dividing each of these factors by the 8 we slid over. Okay, it's always divide by the number that was the slider. Now 36 over 8 simplifies to 9/2. So we have 2 times m plus 9 over 2, and 6 over 8, we have -3/4. Okay, again, we don't leave these as fractions. We have to do what's on the bottom comes up in front of its variable. So bottoms up, that's the fun part. So we have 2 times 2m plus 9 times 4m minus 3. Ta-da! Okay, our last 2 examples in this set, we have on number 19, 9x squared minus 12x plus 4. Okay, I have this 9 in front of x squared. I'm checking, can any part of 9 come out as a GCF? No, it cannot. So we're going to take the 9 and we're going to slide and multiply it over to 4. So that will leave x squared by itself with a coefficient of 1 now. Beautiful. Minus 12x, and 9 times 4 is positive 36. So now we'll do our factor tree. We're looking for two numbers that multiply to positive 36 and add to negative 12. Okay, so what are those two numbers going to be? Okay, well, negative 6 and negative 6. Two negatives multiplied to a positive, they add to a negative. So what we're going to do is have x minus 6 times x minus 6 in parentheses. But if we slide, we must divide. We're dividing each of these by 9. Then we simplify if possible. 6 over 9 simplifies to 2/3. So we have x minus 2/3 times x minus 2/3. And then we do bottoms up. The 3 in each of, goes in front of x. So we have 3x minus 2 times 3x minus 2. Now if you noticed, some of you probably already caught on, these are two of the same exact factors. We have two 3x minus 2's. So we could write this, and we should write it as 3x minus 2 all being squared, because squared means there's two of the same factor. Okay, last one in set 3, number 20. We have 8y squared plus 56y plus 96. Again, I have this 8 in front of my y squared. Check first to see if it comes out as a GCF. Does 8 go into 56? Yes, it does, actually, 7 times. And does 8 go into 96? And on some of these, you might have to use your calculator, and that's always a great idea. And it does go evenly into 96. So the nice thing is it can come out as a GCF. If it all comes out as a GCF, you don't have to slide, which is a little bit easier. So we're going to get y squared plus 7y, and 96 divided by 8 is 12. Okay, and that 8 goes on the outside of the parentheses. Okay, notice there's nothing in front of y squared, so if you don't have to slide, you're just ready to do your factor tree now. We're looking for two numbers that multiply to 12 but add to 7, and that would be 3 and 4. So we are going to leave 8 as a GCF on the outside, and we have y plus 3 times y plus 4. If you don't slide, you don't divide and do bottoms up. Okay, it was just a GCF, so this was done. So GCFs are a little bit quicker than sliders. Okay, we are on set 4 now. We're factoring. This is the last type of factoring that we're going to do for now, and this is called difference of squares. Now, the way to recognize difference of squares, I didn't mean to do that. Difference of squares, there will be only, two terms in the problem. And both of these terms will be perfect squares, and there will be a minus sign in between these two perfect squares. And again, we did talk about this when we did our Algebra 1 review. So looking at 21, we have x squared minus 4. Two terms, x squared and 4, and we have that minus sign in between. What happened here is, notice we have the a value, which is x squared, and we have the c value. We're missing the b. We do not have an x value, and that's another way to recognize this. There's not a regular x or just a regular y. Okay, you have the squared and you have the constant. So then you can use difference of squareds, which is very quick. You're going to turn this, again, it has to be a FOIL problem here as well. And notice that there is no GCF yet on these problems, but we make two sets of parentheses. This is just the standard method when we do it. One set has a plus sign in the middle of the two terms that go in here, and the other will have a minus sign. Now, how do you get the terms that go inside? Well, because we're dealing with two perfect squares, we can undo perfect squares by taking the square root. It's wonderful. So I think, what's the square root of x squared? Or what value times its own self made x squared? It was x times x. So we are putting 1x in each of these parentheses. Okay, because x squared was first in the problem, it goes first in the parentheses. To get the second value in each set of parentheses, I take the square root of that second term. The square root of 4, that was 2 times 2. So 2 goes in each of these. The answer in factored form is x plus 2 times x minus 2. Now, let's see why that works. Let's see if I FOILed this out. If I have x plus 2 times x minus 2, and we FOIL it, we get x squared, x times negative 2 is negative 2x, and then we do plus 2x, and 2 times negative 2 is negative 4. Because we did those, one gets a plus sign, one gets a minus sign, the middle two terms always cancel out. Negative 2x and positive 2x are gone, and we're left with the original problem, x squared minus 4. So difference of squares, if you recognize it, if you train your brain to do that, you're going to love this type of factoring because it's the fastest. So let's look at 22. We have y squared minus 81. Again, we have just these two terms. There's no GCF to take out, but I recognize that y squared, anything with an even exponent is a perfect square. Okay, 2, 4, 6, 8, 0, ending. Perfect square. 81 is a perfect square. It's 9 times 9. And so that means I can make two sets of parentheses. The first set I'm going to put plus, the second minus. You could flip-flop it. It works the same. I get the first term, y squared, I take its square root. That was y times y. So 1y goes in each of the parentheses. Then I take the square root of my 81, and that was, again, 9 times 9. So I put a 9 in each set. My answer in factored form for this is y plus 9 times y minus 9. Okay, number 23, I have 9x squared minus 25y to the 4th. We're adding more things in here, more coefficients, more variables, but notice there's still two terms that met that criteria. I've got a minus sign in between these two terms, which is necessary, and your variables are perfect squares if they have even exponents. So x squared, 2 is even, y to the 4th, that 4 is even. And my coefficients, 9 and 29. Okay, everything in this is a perfect square. So we're meeting all the criteria. So still make two sets of parentheses. One we have a plus sign, one we have a minus sign. That's how we don't have a b value here. They canceled out because of the opposite signs. I take the square root of that whole thing, 9x squared. The square root of 9 is 3. The square root of x squared is 3x. So that was a 3x times a 3x. We put one of those 3x's in each of the parentheses. And then I'm going to look and take the square root of 25y to the 4th. The square root of 25 was 5. The square root of y to the 4th, you divide the exponent by 2 to take its square root, by the way. So that would be y squared. So what that was 5y squared times 5y squared. So we just put one of those in each set of parentheses. And we're done. It's 3x plus 5y squared times 3x minus 5y squared. 24, m squared n squared minus 49. Okay, this m squared n squared, those are both two perfect squares together, so that makes that whole grouping term a perfect square. 49 is a perfect square, and we got our minus sign in between. So two sets of parentheses, plus sign, minus sign. We're taking the square root of the whole first term. So the square root of m squared n squared is, okay, mn. We had an mn times another mn. So mn, mn. And then I take the square root of 49, and the square root of 49 is just 7. So we just put that was 7 times 7. So 1 7 goes in each. So our answer is mn plus 7 times mn minus 7. Okay, 25 and 26, again, a little bit different. You know, we always have to mix things up just a little bit to give ourselves a challenge, because challenges are fun, sometimes, I've heard. So on 25, we have 72r to the 6th minus 2s squared. Now notice I do have the two terms. I have the minus sign in between, but I do notice that 72 and 2 are not perfect squares. But I do notice that they have a common factor. They're both even. So you should always check, okay, if things don't look like they're working out, is there a GCF that could come out of the terms you're working with? And there is a GCF here. 2 is a GCF. So no matter what method you're doing, GCF can always like sneak up and be a part of it. So we're always on the lookout for GCF. So I'm dividing 2 out of each of these factors first. 72 divided by 2 is 36. And we still have that r to the 6th. And then we're dividing negative 2s squared by 2, and that would be negative 1. So I don't need to put it, s squared. Okay, and then we just leave that 2 on the outside. Now looking at what we have left on the inside, 36 is a perfect square, and r6 is a perfect square because 6 is even, and s squared is a perfect square. So when I took out that GCF, I resulted in having two perfect squares with the minus sign in between. So now I can do difference of squares to what's inside. We still don't lose that GCF that we put on the outside. I have 2, then 2 sets of parentheses, plus sign in one, minus sign in the other. I get those answers or those terms that go inside here by taking the square root of each of the terms above. The square root of 36 is 6. The square root of r to the 6, we divide the 6 by 2, and we get r cubed. So we would have had 6r cubed times 6r cubed. That gave us 36r to the 6th. So we just put a 6r cubed in each set of parentheses. Then we take the square root of s squared. Well, again, divide that exponent by 2. 2 divided by 2 is 1, so that was an s times an s. So 1s goes in each set of parentheses. Our answer is 2 times the factor 6r cubed plus s times 6r cubed minus s. And our last one, 26, 2a squared b minus 32a to the 4th b. Again, I do have 2 perfect squares, or I have 2 terms, but I don't have perfect squares yet. But let's see if I can get that after I check for a GCF. So I see that 2 and 32 are both even. That tells me I will at least have a number portion of GCF. 2 goes into 32 and 2. Then I check my variables because that's something we should always check for. On 25, I didn't take any variables out because they didn't have a variable in common. But we have an a squared, a to the 4th. They both have a's. If we have 2 a's and 4 a's, the most we can take out of each is 2 a's, a squared. And then they each have 1 b, so I can pull that b out of each of them. So now we are kind of going back to step 1. I'm dividing that out of each term. And 2a squared b divided by its own self, 2a squared b is positive 1. That always happens when you divide something by its own self. And then my second term, negative 32 divided by 2 is negative 16. 4a's take away 2a's is a squared, and b take away b, there's no b's left. So we wrap that up, and again, GCFs always go outside the parentheses. What we are left with inside the parentheses, okay, all of this business is 2 perfect squares with a minus sign in between. So we're going to be able to do difference of squares to what was inside. My GCF, he just keeps coming down on the outside. We don't lose him. So 2 sets of parentheses, opposite signs, and taking the square root of each of these terms. Don't forget that 1 is also a perfect square. What is the square root of 1? Okay, it's 1. It was 1 times 1. So we put 1 in each set of parentheses first, and then I'm taking the square root of 16a squared. Okay, to get a 16a squared, I would need 4a times 4a. So we're putting a 4a in each of these set of parentheses. So it was 2a squared b times 1 plus 4a times 1 minus 4a. Okay, factoring. Don't give up. You will get better the more you practice. I will help you. We will keep working on this. It's something that we use like all school year long. And again, like I said at the beginning of the video, it is used in all your future math classes if you plan on continuing on with math and higher fields in college. All right, so good luck.